Then you try to see if you can simplify, and the primary way to simplify is by factoring this. So you need to know, first of all, what's the easiest thing to factor here? We want to factor this thing. So what does that turn into? What's the bottom turn into? X minus 1. Correct. X plus 1 times x minus 1. And you need to remember how to factor this. And some of you probably haven't seen this before, which is unfortunate, but it is factorable quite nicely. Actually, anything is factorable, but this is factorable nicely. You just have to remember it. In particular, this is really important. In particular, you really want which factor on the bottom to cancel. You really want x minus 1 to go away, right? So you want to turn this into x minus 1 times something. You want to turn this right here into x minus 1 times something. Let's call it, I don't know, q. I understand there's an answer, but we need to figure out how we work that out. Do you understand why that's what we want? We want that because if we can do that, you can cancel out x minus 1. Do you agree? So we want this to equal x minus 1 times some q value, right? So if I gave you this and I said solve for q, what's the first thing you do if you want to solve for q? What does q equal? X cubed minus 1 divided by x minus 1. That's not the form we want it in, though. We want to be able to write that differently. So you need to remember how to do. Does anybody know what the topic is we're now getting back to? Polynomial what? Yep. Specifically, they call polynomial, and it's kind of irrelevant, but polynomial long division. But it's polynomial division. So if you do polynomial division, you can watch this and see if you remember it at all. You do the division. You're doing x cubed, and you have minus 1 right here. Does anybody remember what you have to put right here? You have to put all the missing terms. What are the missing terms? What's not there that's really kind of there? Plus 0x squared plus 0x. Okay, so now you look at the leading term. The leading term here is x cubed. The leading term here is x. What's x cubed divided by x? X cubed divided by x is x squared. You put the x squared just above where it's supposed to be. Now you do what you do in long division. You multiply, so you do that times x is cubed and negative x squared. And after, this is just like long division, you subtract, right? What's x cubed minus x cubed? The whole point of it is to get rid of it. So now, what's the only thing left? Not negative, because you're subtracting a negative, it's x squared. Now you bring down the 0x. The new leading term is x squared, but this one still is x. So you end up with x plus x. You multiply and you get x squared minus x, like this. You subtract, and what are you left with? Drop down the negative 1. The leading term now is x, so it's x over x is 1. I'll go back in a sec. 1 times x is x. 1 times negative 1 is, and what are you left with? That's the remainder. Remainder of 0 means it divides evenly. So what is question mark equal to? Plus 1. X squared plus x plus 1. So what this means, and I'll explain that one more time, it means that q is equal to x squared plus x plus 1. What cancels now? The x minus 1's cancel. Now what can you plug in? You plug in 1 into this, you get 3 over 2. You get 3 over 2. Remember, it's always leading over. The key to division is just leading over leading. That's the key to division. Leading over leading. What are the leading terms here? The leading terms are here, here, and there. And what's the nice thing? It's 0. If it wasn't 0, what does that mean? It doesn't divide evenly. It's not a factor. It doesn't divide nicely. Exactly.
Then you just put the remainder over the x.
Well, plus 0 over x minus 1. But in this case, what's 0 over x minus 1? 0. If you had a remainder, it would be the remainder over x minus 1. That is absolutely correct, yes. But in this case, did we get what we wanted? Yeah. You hope that was true. If you know something is a factor and the remainder comes out to 7, what does that mean? You made a mistake somewhere. Let's say you were sure that something was a factor of another thing and you did division and you ended up with a remainder other than 0. It means that there's a mistake in your work. Do you understand what I'm saying? Okay, so what could you do to get an idea of what the answer is? You could make a table, right? If you make a table and you get a nice clean answer, if you make a table and you come up with an answer like 7, that generally means there's a good way to do it algebraically. It might not be too easy, but if you do it and the answer is like 0.6489456554, it might be a little harder to do it algebraically. But when you get it, like for example, when you use the quadratic equation, and the quadratic equation gives you answers out of 1 and 5, what does that normally mean about the quadratic? It's nicely factorable, right? Similarly here, if you use your calculator to generate a table and you get a clean answer, that probably means there's an algebraic way to do it. I'm going to rewrite this a little bit and see if you can see what I mean. I'm going to rewrite this. It's the same exact thing, but I'm going to change it just a tad. Have I changed anything? No. What is 3 squared?
9.
What is the square root of t squared? T. What do you now see on top? What do you see on top? You see the difference of, yeah. I rewrote the top. I didn't change, did I change the values? No, but I put it into a form that it's easier to see what's going on. The reason I did that is, can you plug in 9 into the denominator? So I really want to cancel out the 9. I want to cancel out that 3 minus root t. So somehow I wanted to get the, and then I said, wait a minute, what is 9? 3 squared. What is t? The square root of t squared. What does that mean? You can rewrite this as the limit as x goes to 9 of what? 3 minus root t times 3 plus root t. Remember, everybody? A squared minus b squared is equal to what? A minus b times a plus b. Yes, c comes after b, but we don't necessarily always have to write it that way. A plus b, right? So this, now why really helpful? Because now you can cancel, and specifically you're canceling out the thing that you didn't want there to be in the first place. So now you're doing the limit as x goes to 9 of 3 plus root t, which is equal to what? 6. Done. This is a little tricky. This is a little tricky because usually when you're looking for the difference of squares, you look for squares, right? But you have to realize, does it have to specifically say square to be a... No. For example, if you had something to the 8th power minus something to the 4th power, those are nice squares. Actually, any subtraction, any difference is actually a square. It might not be a nice one, but it is. Anytime you anything is a square. Can you take the square root of anything? Yeah. Is it necessarily a nice square root? No. Can you factor everything? Can you factor everything? Yes. Is it necessarily nicely factorable? No. A function f is continuous at a number a if the limit as x goes to a of f of x is equal to f of a. So for example, let's say I gave you this picture right here, and I said this value right here is y equals L, and this right here is x equals a, and I'm going to fill it in right here, and I'm going to say that this value right here is y equals k. Given this picture, can you tell me what's the limit as x goes to a of f of x? And this is f of x. What's the limit as x goes to a of f of x? Not a trick question. What is it? It's L. What is f of a, though? K. K does not equal L. So is f of x continuous at x equals a? No, it's not. If we move that point down and we filled in this dot, would it be continuous? Yes, but it's not. We okay with that? So the 3 things that you have to check for are, this definition implies 3 things. F of a is defined. The function has to be defined at that value. 2, the limit has to exist. What happens if the limit does this? It comes in at different places. The limit doesn't exist, so therefore, is it continuous there? No. And it also implies the last thing, which is the limit as x goes to a of f of x is f of a. Those are the 3 things it implies if I say a function is continuous at an a value. A key thing, though, is a function is made up of how many points, generally speaking? How many points? An infinite number of them, correct. So can you prove a function is continuous by saying it's continuous here, 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 here? Can you check an infinite number of points? Really? You have an infinite amount of time? Can you check an infinite number of points one by one? No, you can't. The definition of a continuous function is a function that is continuous on its domain for every point that's in its domain. Can you check them one by one? No, you can't. You can't check them one by one. But if you know about epsilon delta proofs, can you prove continuity? Yes, you can prove continuity. The first big thing was, what's the easiest way to define a continuous function? Can't pick up your pencil when you're drawing it, right? The second big thing about continuous functions is they're continuous on their domain. This is really important to write. They're continuous on their domain. So for example, here's a really easy question that you're probably going to get wrong. F of x is equal to 1 over x. What does that look like? Use your hands. What's it look like? Yeah, it goes like this and it goes like this, right? Is that function continuous?
Depending on which number.
Is that function continuous? I'm liking how I did this. I set it up properly. Great. You're at least doubting yourself. You want to say what? What do you want to say? You want to say no. Really? Looks like, can you draw that function without picking up your pencil?
No.
If you have two pencils.
If you have two pencils and two hands? Wow, okay. Killing my definitions here. No. So it looks like you want to say that that's not continuous, right? But here's the key thing to remember. A function is continuous if it is continuous on its domain. What's the one x value that's problematic? 0. Is 0 in the domain of that function? No. 0 is not in the domain of that function. Can you plug in 0 into that function? No. 0 is not in the domain. So when you are asked the question or see the question, is this function continuous? You ask yourself, is it continuous on its domain? You don't look at the numbers that are not in its domain. So is this function continuous? It is. It is. That function is continuous because at every point, there's no holes, and the limit at every point is the function at that point. Are there any holes in that thing? No. You don't look at x equals 0 because 0 is not in the domain. So the first thing is, can you draw it? Not picking up your pencil, but you're only looking at the domain. The reason this is important is because it messes up even the best. They should not be totally new. You know what a polynomial is? Any quadratic, any linear function, any cubic. Powers have to be positive whole numbers. Coefficients have to be real numbers. What's a rational function? It's a polynomial over a polynomial. Yeah, ratio, good. Root functions, anything with a radical in it. Square root of x, cube root of x. Trig function, are we cool with trig functions? I mean, do you know what they are? I'm not saying do you have nice, happy, joy thoughts about them, but do you know what they are? Yeah. Inverse trig functions, you might have less happy feelings about those, but do you understand that they exist, like inverse tangent, inverse cosine?
Yes.
Has nothing to do with the -1 power, even though that's how they write it. Exponential functions, they grow quickly, they go down or up. Log functions you might have looked at. Here's the key. Those families of functions are continuous on their domains. If you see a log function, you can now say it is continuous on its domain. These are all continuous. Yes. And sorry, the pen is a little cranky today. Continuous on their what? Domains. This is important. Their domains. On their domains. Exactly. So what that means is, if I gave you, for example, let's say this function right here. If I gave you this one, f of x, and I said, is this function continuous? What do you say? Why? Because it's made up. No, it's not a rational function, actually. It's made up of functions that are continuous. If you're only using continuous functions, can you somehow make it not continuous? Not really. It's really hard to do. The real question is, where is this continuous? And we know it's continuous on its what? So if I asked you where this is continuous, what are you really finding?
Negative squared.
What are you really finding? No, not the answer. What are you actually finding? The domain. So if you want to know where this thing is continuous, you're trying to find the domain. So the question is, I'm going to give you some alone time just with yourself. I'm going to give you 1 minute here. What is the domain of this function? Is that x squared minus 1 cannot be 0. So x squared cannot be 1. So x cannot be what? Plus or minus 1. So there's the first thing you know, correct? ln x. What's the domain of ln x? What is it? X such that x is Greater than 0. That's correct. Can you plug in a negative number into a logarithm? No. Can you plug in 0 into a logarithm? No, you can't. Not defined. So here's the second part of the domain. This entire question comes down to, do you remember anything about this function? This is not equal to 1 over tangent x. No. No. Not. It's not cotangent. Do you remember what it looks like by any chance, those of you that took trig, which is all of you? Do you remember? If you don't, let's graph it and come up with the picture. If you graph it, ready, I'm graphing it on my magical calculator here. It looks like this. That's what inverse tangent looks like. Dude. What? Tangent, regular tangent looks like this. Okay, so here's the question. What's the domain of that function?
It's the range of the original.
Ah, exactly. You're so good, Casey. That is correct. You get a gold star for saying that. Remind me. The domain of this function is what? All real numbers. Or, as I like to say, ARN. Okay, so we have all real numbers for one of the functions. We have this for one of the others, and this for the third. The domain of the whole thing put together is where those overlap. Ah, exactly. So the domain is going to be, ready? There's two ways to say it, and I like the way you said it better than how I was going to say it. It's from 0 to 1, union with 1 to infinity, right? Another way to say that is this. X, sorry, I got to get this back. Another way to say that is x such that x does not equal 1 and x is greater than 0. It's the same thing. Do you understand why? You have three different functions that are glued together. Three different things. You find the domain of two of them and the restriction that's placed by the denominator, and you find where they overlap. So here's the thing. Functions that are built out of these families are continuous everywhere in their domain. So if you're ever asked, where is this function continuous, what are you really finding? The domain. You're finding the domain because you know that those families of functions and every combination of them are continuous everywhere in their domain. Correct. Okay, let's